Hello, so this is Sahib from Group16 and welcome to our presentation. So right now going to give a brief overview of the agenda of this presentation. So we're going to give a basic introduction and a background and what entails in what are the concepts used by us in this project and what was some related work in the to what we've done. To go beyond that, we're going to talk about how we want to move the key idea of our project, which is moving computation to the edge of a network. So we're going to discuss a few concepts regarding that. And in the end, we're going to talk about a proposed solution with a system architecture and the entire machine learning model and how we plan we have deployed it and extensions we think we need to do as we go along. So over to Aisha to take it over.
Hello everyone, my name is Aisha Shahid and I'm from Group16. I'll be going over why we chose edge computing for host-specific ML models for our system. So the main reason was that because yes, I know that we do a lot of computation on the cloud because of lack of resources and issues like battery levels and stuff like that. But today in a world where intelligent devices like cell phones, smartphones, smartwatches, refrigerators that have a lot of computing power, these intelligent devices are very ubiquitous and we need to make use of them. So what we try to do is we move the computation from the cloud towards the edge. This is called edge computing. So, why do we do this? A, because when we do computations in the cloud, when we transfer the results over the network towards the edge host, that takes up a lot of latency because there's an entire routing distance that it needs to cover. Moreover, the quality of service is also degraded because for high frequency trading, markets like the stock market and for low latency applications like video streaming, video calling, and maybe autonomous car maps and stuff like that, you cannot incur latency. So this is something that is not acceptable. And moreover, not only are you taking up a lot of bandwidth, you are also running into bottlenecks. You are also consuming a lot of energy, which is pretty inefficient. So if you move all of this near the edge in the network, that will save you in all of these categories. So edge computing is no big thing in today's world, but what kind of related work happens in the field? I'll go over that. So you have mobile cloud computing. So what it does is, which is similar to what we are going to be doing, it puts a partial part of its computation in the cloud and the other chunk into the mobile. So for example, the load distribution, the load balancing goes into the cloud part and the rest of it goes into the entire computation that is actually supposed to take place goes into the mobile part. Similarly, we have fog computing that was introduced by Cisco. So what it does is for large data centers and centralized computing, it works at the network level and it has to get the cooperation of the network providers and leverage the location and location awareness to get low latency, all of the data which is only available through the network providers. Then comes in mist computing. Mist computing is another sort of edge computing in which it's a three-tier framework that consists of the mist devices that have about four layers. The client layer, then the mist layer, then comes the fog layer. So it's basically also called a fog cloudlet and a cloud layer to provide the power node computation near the edges on the network. So since we have all of these, so why did we decide to use edge computing of the kind of model that? So in out of all of these, after studying all of these, we decided that we would, like the MCC framework, we would have partial computation taken to the centralized server. Like it will handle all the load balancing, it will decide where the requests would go, and it will also be giving information about to the client about which edge host to connect to. So that part of the computation goes towards the server, but the part where the ML model is actually run and the computation takes place actually goes to the edge. Then we also had the opportunity to put fog computing into this. We did not because fog computing requires a lot of additional hardware to be deployed and you need for the geographical distribution and fundamental architecture. So it requires a lot of cooperation between the network providers. It is a level at which we are not functioning right now, and we do not need to go over all of the issues of dealing with the network providers and going on such a massive scale where we have to incur extra costs for additional hardware. So we let go of fog computing. And then the question comes why we did not use mist computing. So we did not use mist computing because, yes, it has a lot of large data sets, just like we're using for ML models for training and everything. But it requires centralized servers in a distributed environment. At this stage, we do not need data centers. All the more reason we're trying to reduce the computation from the data center, but rather at the edge, not at a centralized location like a cloud, so that we can save up efficiency, we can save up cost, we can save up energy. So for all of these reasons,
Hi everyone, my name is Devansh and I'll be discussing the system architecture of our application. So basically, our system will have three main components. It would have the client, it would have the server, and it would have the edge node. So basically, the edge node would house the computation models that will be used to generate the response to the requests that come in from the clients. The server would be responsible to keeping track of all the edge nodes that are active in the system and that those edge nodes that can handle the requests. It would also be doing the computation or running the algorithm to find the edge node that is the best fit for handling a particular request that comes in from a client. So basically, when a client sends a request, the server receives it. It does some computation, it runs an algorithm to find the best edge node to handle that particular request. The criteria it takes care, it considers is that it considers the load on each of the edge nodes, and it considers the latency between the communication between the client and the edges. The server, once it decides the edge node that should be contacted by the client, it sends the response to the client. That is basically the address of the edge node. The client then communicates with the edge node using the address and sends the request. The edge does the computation for the particular request and sends the response back to the client. When the edges join the system, they send in a status report to the server, and all the edges periodically send the status report to the server, which acts as a heartbeat for the edges. This helps the server to know that the edge is still active and can be used to handle requests. The server will maintain a timeout for these status reports, and suppose a particular edge does not respond to or does not provide the status report to the server within the timeout interval, the server will remove it from its active edge nodes list. So basically, the server at any given point of time will have a list of edge nodes that are there to handle the request from clients. Now, the server will continuously keep monitoring the edge nodes. That is, it'll keep getting the status reports from the edges and updating its own list. But the client can come in and contact the server with a particular request. So as soon as the client comes in with a request to the server does the computation to find the best fit edge node for that request, and it responds back to the client.
Hi, it's Sahib again. So far, I think Devansh has gone over how um, the basic framework and the basic architecture we're using in the client server model, and how requests are floated, how they're redirected, and how they're served. So a key part of it is how does a server choose for a particular client which edge host to redirect to. Now, we so far have implemented part of what we've envisioned as our ultimate plan for this redirection. So as of now, in the current implementation, the server considers two factors. It basically implements the whole thing using by associating a score with each edge host. The score is basically a measure of how feasible it is for to redirect that request to that particular edge host. So we start off by allocating each edge host base score on the basis of the machine learning model it learns. As we know, I mean, as that some models are better than others, And so a model with a higher accuracy, a better prediction model, would probably be perform better than one that doesn't. So what we've done is we've assigned a higher score, higher base score to a model which performs better than the other one. And of course, we have differing models because each edge host is not equal in terms of computation, in terms of storage, in terms of network capacity. So we envision that all edge hosts across the whole system will be differentiated in that respect. So moving along with this, after having a base score, as Devansh earlier illustrated, the server has a method of tracking how busy or how loaded a particular edge host is. So by using this tracking, it also assigns a particular uh, contribution from this utilization to the total score. So you take the base score, you add a higher number if the edge host is very low utilization, and a lower number if it's very highly utilized. And at the end of it, um, the edge host with the highest score, that's the one selected. Now, to ensure that the whole thing converges and we do not have conflicts where two edge hosts have the same score, we have a tiebreaker in which the lowest IP address and port number is chosen. Now, moving forward, what we would want to do in terms of edge host selection is incorporate a sense of geolocation in this, because at the end of the day, a very key part of moving computation to the edge is lowering latency. So we would want to redirect client requests to edges that are pretty close to uh, the client in terms of just geographical location, and more often than not, that would correspond to a fewer network hops. So how we envision to do it is a client request would also include a geotag location to the server. Now, in a practical deployment scenario, all the edge hosts would be sort of clustered in an area. So, as an example, there could be a cluster of edge hosts in Midtown Atlanta, and there could be a cluster of hosts in downtown Atlanta. Now, depending on where client request is, I would probably a client sitting in Midtown. I would prefer forwarding that request to a host in Midtown as opposed to downtown. So and identify like this, we plan to use it to sort of factor in this geolocation idea. So this will again be added to the whole score that the hosts will have from the server, and according to that, again, the host with the highest score will be the one that is selected.
Hi everyone, this is Zhang. I will presenting the following section in our workshop group presentation. In order to test our system with a mainstream machine learning task, we implement the style transfer as a backend task for our system. As the name indicating, we want to apply the style of one image to the other image, and at the same time preserving the content information of the applied image. We refer the style as the color of the image and refer the content as the specific feature of the input image. This topic is first studied by the Leon that published in his paper naming a neural algorithm of artistic style. In that paper, they used a neural network, that to say the VGG neural network, to capture the underlying style information and the content information of image. While the layer is a constructed neural network, giving the input image, the style and content feature can be captured by the convolution neural layer. We then use the captured feature to calculate a loss, and then use that loss to perform gradient update for the output image. The original output image is the same as the content image. In order to perform the style transfer, we want an output image that with a small content loss comparing with the input content, and also have small style loss with the input style image. We briefly illustrate the workflow of the style transfer application. In the first step, there are two images, seeing that the one with the turtle as the content provider and the one with the blue cloud as the style provider. We want to apply the style of blue cloud to the turtle one. We first take the input image and style image and resize them into the equal shape for taking them as an input for the neural network. With a pre-trained neural network, that to say Group16 is loaded, we can calculate the content loss and style loss. By combining the content loss and style loss, we can further perform the gradient update to the output image. After a predefined number of iterations, we stop the procedure and take the output as the output image. We have finished the illustration of our machine learning task, and I'm going to introduce some constraints that we consider in our proposed system. Since a machine learning task is computation intensive, and for different machine learning model, the task itself will impose different hardware requirements to the underlying hardware resource. We should consider the actual hardware configuration when performing the machine learning task. For example, swallow neural network with less convolution neuron layer will need less memory, and also comparing with CPU, using the GPU can train the neural network faster with a given same input size. We should capture this difference in our model selection and taking that into consideration of our system. Thus, we perform several checks when it's to actually choosing the model to deployment. The first, we check the memory size. For smaller memory, we choose swallow model with less convolution neural network for the style transfer. Second, we also check that if there's a GPU available in the server. If there's a GPU, we can select larger image size for training. As for the back-end machine learning task implementation, we use a combination of Flask and PyTorch. PyTorch is a mainstream machine learning platform, and we use it to implement our style transfer task. With the image passed as input, we can use the PyTorch to train our neural network. Since we also want to check the resource usage in the hardware configuration, that's to say the memory and GPU usage, as we stated in a previous section, we also use the API provided by the PyTorch for the resource allocation checks. And also, since we want to implement a client-server function call through the network, we need to listen to the client request and call corresponding method to handle that client request. Given that Flask for this is a light web application framework, we can use Flask for the port listening and function calls. When it comes to the real-time application deployment, there are lots of tears and sorrow. The development issue is all talk for software developer. There are a lot of consideration need to be taken into realistic consideration, including the difference in the underlying operating system, whether the client is the Windows operating system or the Linux operating system, and also we should take in consideration about the actual system setting, such as the path and environments. There are countless failures if the issue cannot be addressed well. The deployment issue can be even more serious for the machine learning-oriented application. Aside from the traditional concern in the software development, the platform environment for PyTorch and TensorFlow, this kind of mainstream machine learning platform, along with the dependency requirement and hardware configuration, impose more challenges. Moreover, due to the possibility of model update and input adjustment, the difficulty increases more. And there are lots of prevailing work for the deployment of machine learning model and corresponding application, such as the TensorFlow serving, that to say the TFX, and the Clipper. Since we realize there's a possible deployment issue for our application, we want to handle that issue. Thus, instead of relying heavily on the original system setting in the client server, we choose to use a Python virtual environment and Docker for application deployment. As for Python virtual environment, it is a tool to create isolated Python environment, and we can install the corresponding dependency under the virtual environment and without interfering the original system setting. As for Docker, it has set our platform as a service product that uses operating system level virtualization to deliver software in package called container with isolation guarantee. And we also consider the possible difference in the operating system. For Linux, we developed a deployment script for automatically pulling the Docker image with the complete dependency, and our application runs within the Docker image. As for Windows operating system, since we cannot use the Docker for the Windows due to the limit of Docker, we directly use a Python virtual environment script with PyPackage to manage the corresponding dependency for our application. Now it's come to the illustration of our application function. There are two major components in our client side. One is the interface for image uploading, and it will start sending requests to server for the style transfer machine learning task. The other major component is the style gallery that we preload in our application. User can select the style image from the style gallery for following style transfer task. At the initial, there's no image upload. We show the initial look of our application in the left figure. And once the user selects the local image or from our style gallery, it can post the request to the server for the corresponding style transfer. After the transfer is completed, the server will return the transferred image to client, and this process is shown in the right figure.
So here are a few references that we've used to implement our whole the machine learning model. And thank you for watching our presentations. Please do send any queries and questions you would have to the TAs, and we'd be happy to answer them. Thank you.